So today we're very happy to have Professor Meng Cheng from Yale University, who will be telling us about defects and disorder operators in 2+1 dimension, quantum phases. So Professor Cheng, please.
Okay, thanks for the invitation and also the introduction. It's a pity that I couldn't be there in person. So now I guess we're all ready to travel. I couldn't quite see who's there in the room. I guess there are also some people in the audience. So hi to everyone. I'm sure there's someone, but okay, all right. So I'll get started, and please feel free to interrupt with any questions or comments. And I'll be talking about work done in collaboration with these gentlemen. So just to make sure, can everyone see my pointer?
Yes, we see it.
Okay. All right, cool. So Hong Hao Tu in TU Dresden, and also the group of Ziyang Meng in Hong Kong University. So I'll be near the end of talk. I'll be talking about some numerical results from collaborations with Ziyang's group. Okay. All right, so let's. Oops. Okay. All right, so first let me just start by defining what I have in the title. I suspect the audience has a mix of condensed matter and high energy or field theory people. So for this slide, I'll use more like lattice model definition, and next slide I'll try to make some connection with the field theory language. Okay. So I'm thinking about a quantum many-body system, defined on lattice maybe, or you can continue, but with a global symmetry. Okay. And let's imagine that we have this square lattice model in 2+1 dimensions, and there's some degrees of freedom on each side. Okay. And I'm assuming that the system that we are studying has a global symmetry, which is on-site. Meaning that the global symmetry transformation is a tensor product of unitaries on each of these sites. Okay, so here are labels different sites of the lattice, and I just have U of R, a unitary acting on site R. Okay, so this is what I mean by the on-site unitary symmetry. Since this symmetry is defined over the entire system, so we apply the transformation to all sides at once, and that's what we usually have when we talk about the global symmetry. Now, when I say disorder operator, it really just means we apply the symmetry only to a region of the space. So let's say I draw some region on a lattice. M includes a subset of lattice sites, okay? And we just apply the symmetry transformation to sites inside this region M, which I call U of M, and also labeled by the elements G of the group. Okay. And because I define the symmetry to be an on-site one, there's no question how to restrict the symmetry transformation to a certain region of the lattice. So I can do this, and I have a disorder operator associated to this region M of the lattice, and also the group element. So we can do this when M is any region on lattice, and because of the symmetry, this operator is going to commute with everything that's strictly inside M, and only for, say, the term in the Hamiltonian that straddles the boundary of M, this operator U of M might act non-trivially. Okay. So what it means is that this operator M, this operator U of M, really creates a defect along its boundary. Okay. And it does nothing inside M, it does nothing outside, just by definition. So when we have such a defect, we can imagine opening up the defect, although we couldn't do it, of course, with an operator, because when I apply the operator to a region, it really creates a closed boundary. But when we figure out how this defect acts on the symmetry, acts on the system, we could just imagine opening it up, and we get an open line defect with 2 point defects at its 2 ends. And I'll state that these 2-point defect here and there, they carry G fluxes. And this line connecting these 2 points, the line defect, is where the G action happens. When we take the whatever object through this line, it's acted by the symmetry G. Okay, so this is just to introduce the cast of characters on lattice. And now I'm going to basically retell everything in using a more sort of quantum field theory language. So let's now just redo this using field theory. And I'm going to assume that everything 2+1 and the QFT here has a space-time symmetry, so it's a relativistic QFT. And I'm only going to assume that we are, on this slide at least, we're doing it in a Euclidean signature. So it's really a Euclidean space-time quantum field theory. And now, I guess at least, for many of us, symmetry in quantum field theory, due to the work probably from the audience, some of the audience, that we know that symmetry should really be thought of as a topological operator in the quantum field theory, and the usual symmetry is an invertible topological operator. Okay? And here, topological operator just means that we can deform the operator freely without changing its effect, as long as we don't hit any charge. And the zero form symmetry is a topological surface operator, a codimension 1 operator in 2+1 space-time. And here the surface is closed. That is the same as the global symmetry on the previous slide. Now we can also imagine defining this surface operator on an open surface, which will create a defect along the boundary of the surface. And that is this disorder operator. So here are the pictures. So I have a global symmetry defined on a closed surface. Here's just a sphere. And action on the local operator O is basically wrapping the sphere around that point where the local operator is defined. And we can cut this open and define this surface operator on the hemisphere, which creates a line defect, a codimension 2 defect along the equator. Okay. And I can further imagine taking a slice through the space-time. This is a yellow slice here. And imagine intersecting this operator with a spatial slice, that's the yellow plane. And I get 2-point defects, which carries G fluxes, as shown on the previous slide. So these are essentially the same objects, but now down in continuum. Okay. So most of the talk will be, I'll have in the back of my mind some kind of lattice model, because we like to extract information about the symmetry and defects on the lattice. So sometimes the choice of operator, the shape of the region is motivated by the ability to actually do it on lattice. On the lattice, we don't really have the same freedom in a continuum. All right, so this is just to define the objects that I'm going to study. Of course, this is not new, and defects, especially in recent years, have played increasingly important roles in the study of many-body quantum systems or quantum field theory. And they really offer a very natural set of observables, which are not local, but non-local observables to probe quantum systems, many-body quantum systems or quantum field theories. Okay. It provides a very natural way to characterize quantum states that are symmetry-preserving, that preserve the global symmetry. Okay. So include, for example, symmetry-protected topological faces or symmetry-enriched topological faces. And just from a more pragmatic point of view, defects can sometimes do interesting things useful for information processing. That's where I got into this subject. So I think it's nice to show these figures of defects in various 2+1 condensed matter systems. Okay. Although I'm not really going to talk about this aspect of defect. All right. Okay, so just a bit of nomenclature. So as far as I know, this object, disorder operator, even this name was first, haven't digged all the way through literature, introduced by Kandanov and Siva in 1971 in this paper about classical Ising model, and has this object of, has been around for a long time and probably has been studied in under different names. I've heard various names that it's called in QFT twist or monodromy defect. More recently has also been taken up in more like lattice model sort of context and with different names. All right, but I'll use the word symmetry defect. And if it's not clear, I'll try to attach the adjective, the line or point, just to indicate which codimension we're talking about. All right, so this talk will be about, there are lots of things we can study about these defects, but this talk will be about a very simple quantity, which is the expectation value of this operator in the ground state. Okay. So it's just the ground state expectation value of this U of M operator, where M is some region in space. And I'm assuming that, I'll be assuming that this ground state does not break any symmetry, spontaneously or explicitly. And I'm even going to just focus on the absolute value of this object. So I'm not going to care about like what phase factor it has. Just the absolute value of the ground state expectation value. Okay, so just to get some idea of why this is worth thinking about, let's imagine a fictitious phase diagram of the system, some system with a symmetry G, and we can have, broadly speaking, have two different kinds of phases. In one, we can imagine the symmetry is spontaneously broken, although I'm not going to be really say much about this, but we can certainly have a SSB phase, or we can have a phase where the symmetry is not broken or symmetry is preserved. And maybe there's a transition that goes between the two phases. There could be multiple options in each of these phases, but let's just think about schematically this phase diagram, okay, tuning some parameter G. So suppose we have a local order parameter that transforms non-trivially under the global symmetry, and we know this how this operator should behave generally in these two phases. So in a symmetry breaking phase, this order parameter develops a long-range order. That's a defining signature of spontaneous symmetry breaking. And usually, generically, this operator decays with distance exponentially if it's gapped. It could be power law when the symmetry is not broken. Okay. Here, I don't only roll the option when it's gapped. Now, this is textbook stuff. Now let's consider what happens with this disorder operator, applied to some region M. And I'll be assuming that this region is large enough so we can talk about how this quantity scales with, say, the size of the region, okay? And everything should be absolute value. So in the spontaneous symmetry breaking phase, this expectation value, I'll call it disorder parameter, just to mirror order parameter. So this disorder parameter is going to scale exponentially with the area of the region because it's going to change the state everywhere in the system, including inside M. So we create a large difference in the state, and that gives you this area law, area of the M scaling. On the other hand, if we are in the symmetric phase, then this disorder parameter, the expectation value, should scale exponentially only with the length of the boundary, because everywhere inside this region, the symmetry is preserved. And I'll refer to this as a parameter scaling. Okay. So there's some coefficient A1 in front of the L, which is a parameter, and B2 in front of the area. These are non-universal coefficients, which depend on some details of that very short distance. Okay, so a few remarks. First, there's a little ambiguity, well, actually important ambiguity in the definition of this operator U of M, because we only really know without any ambiguity how to define this operator inside the region, because that just means applying the symmetry to the region. On the boundary, there's some ambiguity. So we could modify this operator along the boundary. Okay. And for continuous symmetry, so all of these scaling are for discrete symmetries. I'm sorry, I forgot to mention that. For continuous symmetries, the area law part needs to be modified. For example, if it's U1, then this disorder parameter will scale somewhat differently. Instead of area law, it's L log L due to the Goldstone fluctuations. And I'm going to not talk about the series with gapless lines in the low energy spectrum, such as a Fermi liquid. So it's only gapped or region systems with gapless points. Okay. Right. So this disorder operator actually includes some of the things that we are familiar with, in case that's not very familiar. So includes things like Rényi entropy. This can be thought of as a particular disorder parameter if we represent the Rényi entropy as using the replica trick. Because the Rényi entropy, for example, here I write the expression for the second Rényi entropy, and this is particularly useful in numerical simulations to represent Rényi entropy as expectation value of a swap operator that swap two copies of the system, the two replicas, but only in the regions where we are calculating the entanglement, the entangling regions. So disorder parameter of the cyclic permutation symmetry of the replicas is exactly the Rényi entropy up to some global, up to some constant. So this is one example of disorder parameter, but we could do it for any global symmetry we have. And I'll come back to this example later. All right. So let's now get back to the scaling of this disorder parameter, the expectation value. So on the previous slide, I discussed the leading order scaling, the leading scaling term in the expectation value, which is exponential decay in the parameter when the symmetry is not broken. Okay? And really, I'm going to really limit myself to these two cases. One is where we have a symmetry-preserving but gapped ground state. In 2+1, they can all be described, believed to be described by topological quantum field theories. Another case that I'll talk about is a quantum critical point, and I'll assume that they will be described by a Lorentz invariant or relativistic conformal field theory at low energy. All right, so the leading term is not particularly interesting because of the coefficients are non-universal, but the subleading corrections are somewhat more interesting. So let's talk about the next order correction. Okay, so it will be convenient to actually take the logarithm of the disorder parameter and also put a minus sign in front of it. So the leading piece is this parameter scaling, the term that proportional to the parameter of the region, because I'm already in the symmetric phase with a non-universal coefficient A of 1. Okay. And then the next term will depend on what exactly we are looking at. So if the region is smooth, and in these two cases, or when the system is gapped, the subleading correction should be a constant. Okay. When M is large enough, so when the size is small, it's a bit hard to say exactly what happens, but when the M is large enough, we can say that there's a constant correction. And when this is in the gapless critical point, and this region has sharp corners, then this logarithm of the disorder parameter has a logarithmic correction, log of the parameter, with a universal coefficient, which I call S, sometimes referred to as a corner correction. So both the gamma when it's smooth or when the system is gapped, and also this coefficient of the log correction, they are universal, at least when the region is large enough, or you can say when we really go to the deep infrared for the defect. And these are the universal corrections that we'll be interested in to find out what they actually mean in the various cases. So this gamma was called a defect entropy in a recent paper by Como et al. Last year, and they showed that this gamma, at least when you define it appropriately, decreases monotonically with the RG flow or with the size of the region when it's defined appropriately. And the approach is some constant when the region is large enough. That's the limit that I'm interested in. All right, so for the rest of the talk, I'll first discuss what this gamma should be in the case of a gapped phase, and then turn to this logarithmic correction S in a CFT. So I think it's probably a good point to pause. Wait, see whether
I had a question. So you talked about symmetry operators and about Renyi entropies. They would both have a gamma with the same gamma, or?
No, they will have very different gamma. So
I see.
Yeah,
okay.
yeah, I should probably attach G to all these objects. So this will be different for different, could be different for different symmetry actions or symmetry transformations, and certain is definitely a property of the symmetry.
Okay. But your claim is that it doesn't depend on the. When you say it's universal, you mean it won't depend on the microscopics, but it could still depend on, say, the CFT or, yeah, what will it depend on?
Oh, the universal just mean that it doesn't depend on lots of short distance details, but yeah, that's a good question. So I'll be more specific about what really determines gamma in the next few slides. And S should be a universal quantity associated with a CFT. Hopefully I'll answer this question as we go along. All right. Okay, so let's now focus on the case when there's a gap. So it's a symmetric gap phase. And to unpack the meaning of this gamma, so I need to first take a few minutes to discuss the physics of a gapped phase in 2+1. Okay. So at least it's widely believed that all the gapped phases are described by topological quantum field theories in 2+1 dimensions. And mathematically, a topological quantum field theory in 2+1 can be represented by a pair. First one is a unitary modular tensor category, but no, it really is a mathematical description of the universal properties of anyons in the 2+1 system. And C minus is a chiral central charge, which doesn't really play any role, so we can just forget about it, at least for this talk. Okay. So, so this tensor category is really just a mathematical packaging of the properties of anyons. So at the low energy, the excitations of a gapped system can be described in terms of weakly interacting localized particles, which I call anyons, and they are divided into different types of anyons. So you have a collection of labels for the different types, A, B, and C. Okay. And the fundamental property of these anyons that we can fuse them, we can bring two anyons together and ask what is the result of this composite object? What is the type of any of this composite object? And in general, this fusion will give us a superposition, really, and the more precise term is a direct sum of different outcomes, of different types of anyons could show up when we fuse two anyons together. And this rule of what comes out from fusion is called the fusion rule, and it's written as A tensor B, A times B equals the direct sum of the possible outcomes. And there is a direct sum of different anyons C with a coefficient, and this coefficient is a non-negative integer, could be 0, 1, or 2, although most of the time it's 0 and 1. Okay, so this is a bit of information I need about anyons, and later I'll do it for defects. There are many other elaborate structures in this modular tensor category which we don't really need to talk about. So I'll just keep it to the minimum. If this fusion rule is somewhat unfamiliar, well, what really matter is a quantity called quantum dimension. So we can define it actually without using the fusion rule. And here's a physical interpretation of the quantum dimension. So if I have n anyons of the same type, let's say type A, and they are well separated from each other. So let's say they are far away from each other. And I have just n of them in the system. And we can ask what is the degeneracy of the ground state in the presence of this n anyons of type A. Then the degeneracy scales exponentially with the number of anyons with a base given by the quantum dimension d of A. Okay? So quantum dimension is going to be a positive number greater or equal than 1. So for those who are familiar with the modular tensor category, in the diagrammatic formalism, this d of A can be represented by this loop, which we can intuitively think of as a word line of an anyon, the Wilson loop of the anyons. And if it's a billion, then if d is 1, meaning that the state is unique, when you have multiple anyon, it's a billion anyon, and otherwise non-billion. So this is a basic quantity, universal quantity that we can define for the anyons. Now, this is just how we describe a gapped phase in 2+1 without any symmetry. And let's now also put in symmetry. So for such a gapped phase, anyons, there's an emergent zero form global symmetry, a global symmetry that's always a finite group. Okay? And this finite group includes for example, all kinds of ways that you can permute the labels of anyons while keeping the physical properties invariant. Okay? That's always a finite group. And for any given microscopic symmetry, G, so G is one of the elements of the microscopic symmetry, then we can uniquely associate G with an element of this emergent symmetry group, which means, in most cases, it just means that we can tell how the symmetry G transforms the labels of anyons. It doesn't have to transform, it could just keep the labels intact, but sometimes it transforms. We can find a unique element of that group associated to G. Okay. Now, when we are in this gapped phase and we now put in a G defect, there could be multiple distinct types of defect line here, okay, all carrying the same G label, meaning that when we think of it as a boundary of the symmetry operator, the surface is unique, just determined by what symmetries we are talking about. However, the boundary, there could be multiple distinct choices, and they'll be called A of G. There are multiple different defects that live inside a set of defects, Okay? If we turn this into a lattice picture and further cut this boundary open, then we get this point-like defects carrying G fluxes, but there are multiple different possibilities for these points. The point defect, even though the symmetry line defect is fixed. Okay, so this is a basic, structure of how I think about defects, symmetry defects in the gapped phase in 2+1. Okay. Now let's tie this back to the disorder parameter. Okay. Oh, last thing, actually important, that these defects, we can also fuse a defect just like we can fuse the anyons, and they also have their own fusion rules, and we can define the quantum dimensions of the defects exactly in the same way that we define quantum dimension for anyons. All right, and I'll call them D of A of G. So A of G labels different types of defects. Just to give one example, so let's consider this replica of a certain quantum manifold system where we use to calculate Renyi entropy. So we create n copies of the gapped phase. They're all identical, so we have at least a cyclic permutation symmetry among them. I mean, all kind of permutation, including a cyclic one, and that's the one that's responsible for the Renyi entropy. So since we have n copies, the anyon excitations can be labeled as a tuple of n elements each one for a label of anyons in one of these layers. So I have A1, A2, all the way to A of n. Okay? Each of them is a label of anyons in the ith layer, let's say. And I can define a cyclic permutation, basically just permute the layers cyclically. That will take, for example, A1, A2 to AN to AN, A1, and A all the way to AN minus 1, just a cyclic permutation. We can now study the defects of this cyclic permutation symmetry. We can put in there's a particular defect, which I call the bare defect, denoted by 0 of R. So it's the defect of the symmetry R, and it's labeled by 0, just a convention to call it 0, and satisfy this particular fusion rule. So the detail of this fusion rule does not really matter. What I need a bit later is that the quantum dimension of this defect can be exactly calculated. The dimension, it turns out to be the total dimension of the anyon theory to the n minus 1 power. The total dimension is the square root of the sum of the square of all dimensions. There's another quantity that we can calculate when we know the quantum dimension of the anyons. Okay. And we can get other defects. There are other kinds of defects just by fusing anyon from one layer to the defect, and that will generate all the other defects. Okay, so this is all the defects associated with a cyclic permutation in this kind of system. All right. Now let's consider what's the physical meaning of this gamma. Okay. So heuristically, the picture that the gamma of G, the gamma associated with symmetry transformation G, and gamma, just to remind everyone, gamma is this constant correction when we calculate the expectation value of U of M of G. It's the quantum dimension of the defect, basically. And the reason is that we can roughly think of the defect line created by this operator U of M as a trajectory of a G flux, a point defect G flux moving around this boundary. And that in the TKFT basically is the word line of this point-like defect, and that should evaluate to the quantum dimension of the G point defect, the G flux. Now, the question here that, as we just discussed, there are multiple different kinds of defects. So what exactly is this G defect? When we apply this operator to symmetry transformation to M, what kind of defect we actually create on the boundary? Now, this doesn't really have a completely universal answer because it really depends on exactly how the symmetry acts in this system. But in general, what we can say is that this line operator, this line defect that we create by applying a global symmetry G to the region M can be written as a direct sum of the various defects that we have in this system, A of G. These are like the fundamental types of defects, and any defect can be written as a direct sum of these defects, the basic ones. Just like any excitation can be written as a direct sum of anyons when there's no defect. And these are integers. These P's are non-negative integers, which at this point, we just don't know them. We have to determine them through some more information. Okay. And if this is the case, then gamma would be this P times the sum over all the defects of the dimension of each of them and weighted by this integer P. Okay. So that's going to be the answer once we can figure out what P is. Now, as I said, this P, the P depends really on some more information not available just through the TQFT. Okay. If we don't know anything else about the system, that's all we can say. Okay. But I'll describe one scenario where there's a sort of natural way to determine what P is, and that's quite common, encountered in various examples. So this is the case when the entanglement spectrum of this region. So we are really looking at symmetry acting on a certain region, and we can talk about what is the reduced density matrix on this region, and there's an entanglement Hamiltonian for that region. Okay. And let's assume that this entanglement Hamiltonian or entanglement spectrum associated with the region M can be described by a 1+1 conformal field theory. Okay. Doesn't have to be the case, but it's not uncommon to have a CFT's entanglement spectrum. So here's the assumption that the reduced density operator associated to this region M takes a form of a thermal state of some 1+1 CFT. Okay. And I've chosen the convention that this CFT, the Hamiltonian is the dimensionless Hamiltonian of the CFT. You can write it in terms of the Virasoro generators. And then all the dimensionful quantities are in front. This is the effective temperature. C can be roughly understood as a coloration length of this phase, and L is the length of the region always. But we are really interested in the limit where this coloration length is much smaller than L. So in a sense, we are looking at high temperature of the entanglement Hamiltonian. Okay. So it doesn't really matter what happens at low temperature. There could be a gapped state of the entanglement Hamiltonian low temperature. As long as it's a CFT-like Hamiltonian high temperature, that's good enough for this purpose. So it covers a lot of the cases. Okay, so in this case, once we make this assumption, we can reduce the calculation of this disorder operator to the thermal expectation value of the symmetry operator in the CFT. So we can naturally induce a symmetry action in the 1+1 entanglement Hamiltonian by basically restricting this bulk action to the boundary. Okay. So here U of G is the induced symmetry action in the 1+1 CFT. Okay, so here's, I won't go through all the steps, but here's roughly how we're going to calculate this. I mean, it's probably familiar to many of you. This is a trick that we always use in CFT. When we need to calculate something at high temperature, we use a modular transformation to relate this to low temperature expectation value. So the quantity that we want to calculate here is the thermal expectation value, which we can roughly understand as having a defect, a symmetry action of this U of G along the time direction. So I'm imagining have a CFT living on this circle, spatial circle here, and the vertical direction is time. So it's a space-time cylinder. And the expectation value, we can write it as just this picture, the trace of the U of G on the spatial slice. And by applying a modular transformation, we go to another picture where instead of having a symmetry applied to the spatial slides, we have a twisted boundary condition of the spatial slice twisted by the symmetry G. So it's going vertically. And the relations, to relate these two pictures, we need to apply the appropriate S modular transformation. Okay.
Sorry, which space-time dimension is this S acting in? What dimension is this figure in? I thought U was a surface operator in 3 space-time dimensions.
Yeah, but now I reduce this calculation to the boundary or the entanglement spectrum. So that's 1+1D. Okay.
Just where is the 1+1D theory?
The 1+1D lives on the boundary of this region M. So first, we can write the entanglement Hamiltonian or the reduced density matrix as the assumption that we can write it as a thermal state of some CFT living on the boundary of the system, which is true in many cases. And it's gapped. So basically, I can always write it this way. And here's the assumption that this entanglement Hamiltonian is a CFT, at least at high temperature. So now we reduce this to the calculation in the CFT, in the 1+1 CFT. And then the cylinder is just a space-time of manifold of the CFT. Does that make sense?
Yes, and you have in mind that that CFT is something simple, so that this sum there is finite, and you know what you're doing, and things like that.
The CFT could be. I haven't assumed that anything about the CFT. There's just some CFT that lives on the boundary of the system.
Yeah, but if it's a general CFT, not something, say, rational, then
Oh, okay, that's all right. Yeah, so I'm assuming it's a rational CFT for now.
okay.
Here, okay, let's assume it's a rational CFT. Just to be on the safe side. I don't really know much about irrational CFT. Yeah, I'm assuming that it's a rational CFT. Although I suspect some of the things could be generalized to irrational case, but let me stay on the safe side.
Okay.
Right, so here's some appropriate S transformation matrix element, which I'll give expression on the next slide. But the basic idea that we can do a modular transformation that relates the high temperature to a low temperature, and then we can evaluate the quantity for the low temperature partition function. Okay, so this is a S, which is given by the defect. Now here's a sum over all different kinds of defects, and this line should be the line in the A of G, particular sector of the defect. So we are really looking at a defect Hilbert space where there's an A of G, where we twist the system by an A of G line. Then this S matrix element is given by the quantum dimension of that defect divided by the total dimension, quantum dimension of the Anyang theory. So this is just something that we can work out. And then we can just do the usual thing that same derivation, for example, that goes into the Cardi formula, expand it, and we get this result that the disorder parameter, the logarithm of the disorder parameter, the negative logarithm of the disorder parameter is given by this expression to a leading order up to some exponentially small corrections. So there's this parameter scaling piece that goes like proportional to L, and there's a minus log of D. And now this DG again takes this general form, sum over the defects. Now the sum is restricted to these A of G's with a minimal scaling dimension in the defect, among all the defect sectors. And this P will be the degeneracy of the highest weight state in that sector. Okay. So now these numbers can be determined through some properties of the CFT. So what this calculation really said that once we know the boundary of the system has a CFT, at least at high temperature for the entanglement Hamiltonian, we can determine exactly these P's using information of the CFT, the degeneracy of the highest weight state in that sector. Okay. This is some additional information. This is beyond the TPFT. We need to know what CFT we have.
Can I ask about the linear term in the length in
Yeah.
the logarithm? We talked earlier about how that was scheme dependent, but now you seem to get a very nice answer for it.
That's again because I'm assuming that there's a CFT on the boundary, and it still depends on the correlation length of the system.
But that suggests that there was some natural ultraviolet scheme assumption that you could have put in that would have made the leading term meaningful. I'm just trying to understand, am I reading too much into this linear term, or is it meaningful in any case after you put in some scheme information?
I think it's probably once we put in all this information about the CFT and what's the inverse temperature, it is meaningful because there's an additional scale that you introduced. Explicitly, that's this Cassi, and now there's a meaningful coefficient.
But could you say what it was in the ultraviolet that you did? I guess that's what I'm asking. Like, you've gone to some IR limit where you have a TQFT, and then you're saying, okay, if I have this CFT situation, then I have this nice answer. But what I'm wondering is if the leading term in the defect expectation value can be made meaningful by some kind of property of the ultraviolet.
By some property of the ultraviolet.
What was good about getting this answer from the UV point of view? I mean, from the UV point of view, it looks like you could have just modified UM by anything on its boundary.
Yeah, so I think that what really goes into, sorry, I went too far beyond. So what really goes into this derivation, the UV information is this equation that we can relate the expectation value of U inside M to one that's on the boundary.
Yeah.
And now, once we make this assumption, well, once we have this relation, then there's a nice answer that follows.
But
So
isn't
now
that true? Isn't that true at short distances as well, that formula?
Yeah, that's true at short distance, but you could imagine that we just, just by hand modify this U of m, attaching some Wilson line of any along the boundary, but that will change the right-hand side. You might need to introduce some additional line, topological defect line in the CFT in order to make this equal. And this is like the simplest option that we don't do anything funny on the boundary of M, and this expectation value is simply equal to the trace of the symmetry in the entanglement Hamiltonian. And that should be true at short distance as well.
Okay.
Yeah, so that's well, I guess I'm not sure that really answers the question, but that's the best I can do right now. All right, so let me move on. So just to, I guess I'm running a little slow, so I'll speed up a little bit. So back to this example of replica symmetry. I've already discussed the defects. So now let's apply this formula that I've just derived to this system. And this is a bit of a CFT knowledge, particularly a fact about the permutation orbifold of the CFT. Is that in the defect sector, there's a unique highest weight state, exactly in that bare defect sector, 0 of R. Then when we use that answer, we get the familiar result of the topological entanglement entropy in the Rani, topological entanglement Rani entropy, the log of D. D is a total dimension. Just to give one more quick example, so I think I'll probably skip this just so that I can get to the rest of the talk. But I'll be I'll be happy to talk about it offline if people are interested. All right, so this is about what happens in the gapped phase. So we can relate this to quantum dimensions, with the help of a little more information about the boundary CFT. Okay. Now I'll switch gears and now look at what happens when the system is gapless at quantum critical point. So it's described by a CFT. That's assumption. All right. So again, this is the same picture that I showed earlier on the ordered and symmetry breaking and symmetric phase. We know what they look like, what this other parameter scale, the scaling looks like. Okay, so now the question is what happens at critical point. And now assume that this G symmetry is on the brink of being broken. So the G order parameter has algebraic correlations at the critical point. Okay. So this G really X some way. Let's just start from a 1+1 dimension where we know the answer perfectly. So the negative logarithm or logarithm of the disorder parameter scales logarithmically with the length of that region. And the region is an interval in 1D, so it's just logarithm of the region of the length. And that just says that there's a power law correlation function of the defects. Okay. Now in 2+1, we get, it turns out that the result should take the following form. This is actually the only consistent thing you can write down, consistent with the scale invariance, that the logarithm has a leading piece A of L, and the next term is a logarithm of the length of the boundary with coefficient S. Okay, L is the length of the boundary. I can almost get this by just arguing scale invariance. Now the S depends on, so what does the S depend on? Well, S actually depends on what corners, whether you have corners, whether there are corners or what, exactly is the opening angle of the corners of this region M. So the M could have multiple corners if it's like a square or a triangle. Then each corner has an opening angle alpha. So S is going to be a sum over S of alpha for each of the corners. Okay? And then this S of alpha is believed, this is something that I don't know how to prove, but it's believed to be a universal function of that opening angle. universal in the sense that there's some CFT data, but then the dependence on alpha may be universal. Okay.
What about the dependence on G? On the group element, or what type of defect it is?
Yeah, so that information, it also depends on G. So
Okay.
I've suppressed the G dependence. I'll restart it next slide.
And universal, just to clarify, means it's allowed to change from CFT to CFT, or it's independent of which CFT you happen to be in?
This is a wild conjecture that this dependence on alpha actually does not change from CFT to FC. Okay. But again, this is just a conjecture. Could be wrong.
But sorry, in 1 + 1D, S would have been something like the central charge, or the 1 + 1D?
If it's a Renyi, then it will be related to a central charge. Like, otherwise, it's just a scalar dimension of the defect operator.
But so your conjecture isn't supported by the 1 + 1D example?
Well, the conjecture is only for 2 + 1 because only in 2 + 1 we can talk about opening angles.
Okay.
In 1D, there's no such dependence. All right, so now just to give some of the results that we know about this S. So the same thing has been studied for Renyi entropy for quite some time. And we can actually relate this S for certain symmetries exactly to Renyi entropy if the theory is a free theory, okay, including free fermions. And I'll mention some analytical results for various limits and show a little bit of numerics in other cases when we don't really have analytical control. So the first limit is when the global symmetry is U1. So now let's imagine that the CFT has a U1 global symmetry. So for each U1 rotation, each rotation angle, theta, I can define disorder parameter. So it looks like this. It's parameterized by an angle theta from 0 to 2 pi, so just angle that parameterizes the U1. And it's e to I theta of the charge inside the region M. So it's an integral of charge density over M. And we can write down the scaling at various points, regions on the phase diagram. It has this L log L scaling in the superfluid phase, has this exponential parameter scaling with power law at a critical point, and just exponential in the insulator phase. Now, here's a limit that we can easily calculate when the theta is very small, because when theta is small, we can just expand it and we get 2-point functions of rho, and 2-point functions of charge density in the CFT is universal. There's a central charge, but otherwise it's universal. So this is the limit that we can calculate when theta is very small. And the result is given here. So if you do this calculation, theta is a U1 angle, alpha is an opening angle, and has this dependence. So all the CFT information goes into the prefactor here. So it's Cj is a current central charge, theta is this group element, and then there's a function of alpha. Okay.
But there are higher order and theta corrections, which would depend.
There are higher order theta corrections which we don't know, but at least to this order, it takes this form. That's right. We don't really know the higher order corrections.
But naively, don't you expect them to depend on higher point functions of the current and therefore on a lot of stuff?
Yeah, exactly.
Yeah, so they will depend on higher point functions. But exactly how it's not even clear that you'll get something that scales this way from just perturbably from the higher order.
But so I guess your conjecture is that S only depends on the CFT data and alpha.
That's certainly true, but the stronger statement is that there's a universal dependence on alpha. But that, I guess I don't really have very strong evidence beyond this result.
But I don't understand why can't we just falsify that claim by looking at the 3-point function? Like, won't the 3-point function give you some other function of alpha that will be there? I don't understand that.
Even the 3-point function or the 4-point, the 3-point function is somewhat different because that's effect of I. So I would actually go to the next order, the 4-point function. That's complicated, and still not quite get what exactly it should look like. Yeah, it might be easily falsified once we are able to calculate higher order corrections.
Okay.
Yeah, although we haven't been able to do so. All right, so another limit we can study is when the angle is very close to pi. Suppose that, and then which means that this corner is almost flat, just with a small opening angle, with a large opening angle, but a small deficit. In that case, we can also calculate this S of alpha just by using the defect CFT property. We'll get pi minus alpha squared, with C of D is the central charge of the defect. So we can get the C of D from the displacement operator on the defect, but that's some universal quantity related to this defect. Okay. So again, there's a universal dependence on alpha in this limit. Okay. For U1 defect, we can figure out what the C of D is when theta is very small. So just extracted that from the formula on the previous slide. That's the result. Okay. All right. So these are the general analytical results that one can derive in various limits. Okay. Now, I guess I'm already, since I start 5 minutes later, I'll use a few more minutes to show some numerical calculations on lattice, where beyond these analytical limits, it's hard to do exact calculations. So I'll just show the numerics. Okay. So first example is O2 or XY CFT. And the lattice realization is not particularly important. Details are not particularly important. I guess what we need to know is that it's a lattice model on a square lattice with spins or rotors on each side. So we can take the region. The natural thing to do is to take a region to be a rectangle or a square. So we'll take it to be a square of say L by L. And then define the disorder operator of the U1 symmetry on that region. So here's some just data from Monte Carlo simulations, which was done beautifully by Xiang's group. And the figure shows, actually what's called X, it should be U. The main figure shows just how it decays exponentially with L on the semi-log scale. The inset shows the S extracted from fitting this with the scaling formula. Okay. And there are different colors represent different system size, and it seems to converge well on this black line. Okay. This is a dependence on theta. The alpha is fixed to be pi over 2 because we take a square region. Okay, so we can fit this to the formula and extract the current central charge when theta is small. Remember that when theta is small, there's a coefficient proportional to Cj times theta squared. And we can just get the result from the fit, and agrees very well with the known value of the current central charge, maybe from bootstrap or large NX calculation. Okay. So I kind of said that what we do makes sense. I'll discuss one more result about numerics, which we don't really know how to understand theoretically, but I think it's kind of at least intriguing. So this transition, so we just, on the previous example is a conventional sort of Ginsburg-Landau transition, but let's apply this to a transition that's not in the Ginsburg-Landau type. This is the deconfined quantum critical point. It's supposedly a continuous transition between two different symmetry breaking states, meaning that the states breaking very different kinds of symmetries, which will be forbidden in the Landau classification of phase transitions. Okay. The particular example that we looked at is a neo to VBS transition. So it's a spin 1/2 model on a square lattice, and it's supposedly a continuous transition between the antiferromagnetic new order and the valence bond solid order. Okay, so one breaks the spin rotation symmetry, the other breaks only the lattice symmetry. And the proposal that was made long ago by Sentil et al. Is that this theory this critical point is described by a bosonic, a CP1 model, essentially, a bosonic spin-ons coupled to a U1 gauge field. And it was proposed that there is this particular spin model where this transition is realized by tuning a parameter, this Q over J. Okay. Now, there are lots of questions surrounding this transition. It was believed to have emergent SO5 symmetry. It's nearly conformal, at least in this model, up to the largest system size that's accessible, but with unusual finite size scaling, drifting, and it's the biggest issue is that it's inconsistent with the bootstrap bounds. So there's probably not a unitary CFT, and there are various ways to understand this. So I just want to show the calculation of the disorder operator associated with a spin rotation U1 symmetry in this model. Okay. So microscopically, the lattice model has the SO3 spin rotation symmetry, and also the C4, and also translation symmetry. C4 is the point group. So I'll just focus on SO3 and actually just the U1 rotation, which can always be written in this form up to conjugacy, okay? Just rotation around z-axis. And we can do the same calculation and find this S of theta when the region is a square, okay, as a function of the U1 rotation parameter theta. So unlike the previous case, if you still remember the curve, which bends upwards, now this curve actually goes up a little bit, then goes down, becomes negative when theta is close to pi. If we believe this numerics, there are subtleties in extracting this S of theta, but if we believe this result, this is actually not possible in any unitary CFT, because that's something can prove that in a unitary CFT, this S theta equals pi has to be positive, otherwise we violate unitarity. So we see not just a small violation, we see a quite finite violation of unitarity even though we are still in the conformal window. Okay. In the system size where this looks like continuous transition. Actually, we find similar results for Raney entropy, although in that case, the system size that we can access is much smaller. So we don't really understand this result. It's just something that we observe in numerics. So
sorry, in the previous slide,
yeah,
you said it's for the Z2 disorder parameter, but isn't this a U1?
Yeah, but if we take theta to pi, that's a Z2 symmetry. So this result only applies to the theta equals pi point. Maybe it's possible to extend it beyond it, but at least that's what we need.
I see, thanks.
Isn't this consistent with the interpretation that the transition is not, in fact, second order, but it's just close to being second order?
Yeah, so that's broadly consistent because it just said that the unitarity has to be violated. There cannot be any unitary CFT description. But if we try to match the details, there's something a bit uncomfortable, at least, because this violation is not small. So the idea is that this working RG or the complex CFT scenario is that it has some vague sentence that the CFT is controlled by something very close to the real axis. That's why we get this large length scale, etc. But if that's the case, then we should expect to see a small non-unitary correction to S. However, we see something that's quite negative. So I'm not sure this is all consistent. There's the honest answer that we don't really understand it, but it's not entirely obvious that we can interpret within this complex CFT scenario.
And this is still for a square shape?
This is for square shape, yeah. That's all we can do.
So using your kind of function as a function of alpha. So have you tested whether other shapes with more corners, etc. Still
on the square lattice, it's very limited by the lattice geometry. On the square lattice, we can only do pi over 2. If you can come up with a model on a different kind of lattice, maybe we can do other angles. And we are looking at other models as well.
So how do you know that it is large, negative large, compared to something that you expect it to be?
No, okay, yeah. So
large or small?
Yeah, so indeed, this is somewhat vague because no, we don't really have something absolute to compare with, but this model is continuous, at least looks continuous. There's no conventional signature of first order transition up to system size of order like 200. And if we believe maybe even larger, so it's not clear. It's not clear. Yeah, that's a good point. We don't really have a nice comparison of which one's large, which one's small. But numerically, we don't observe anything that's first order in this transition for this particular model, except that things are drifting. Other than that, there's no clear signature of first order transition. So it seems like we are still in the conformal window. But if that's the case, so yeah, so we still need to understand better how this complex CFT plays out for this quantity S. But I guess what I was trying to say that it's not entirely obvious that it's consistent with this picture. We need to do more checks. Okay, so I guess this is all I want to say. Sorry that taking a bit longer, and thanks for your attention.
So I had a question. You're focusing on defect operator. That's basically the integral of the charge, and I guess that's pretty nice, or the charge density, and that's pretty nice because in your, you know that you can integrate it over a surface, and it's just going to give you something on a line.
That's
but
for the CFT, at least.
Yeah, but in the CFT, you kind of could have integrated any local operator along the line and studied, similar questions. I wonder if you.
Yeah, I guess so. I mean, you can integrate any local operator along the line.
For example, the charged operator, like in the models you looked at, you could have integrated down like the charged operator along the line, and presumably there's some similar physics.
Yeah, well, of course, no. When the CFT has line operators, if they're like Wilson line, we can just ask the same question for the Wilson line. I guess in this case, I'm thinking about this particular operator because it's a nice relation with the global symmetry, and we can relate the results to various properties of the global symmetry, like in this case of the current central charge. And we can certainly.
But I wonder if that's just more general. Like you could have integrated any operator along the line, and then your observable would have been fixed by the few first point functions of that operator to leading order.
Yeah, it could be. Although, let me go back a little bit. For example, this particular calculation there, that's a good question, but this particular calculation, what I want to show, this particular calculation I did here is expanding out. For example, for this particular result, we expand out this U to say second order and get 2-point function of rho. So this corner term comes out from the integral of the 2-point function over the entire region. So it's not entirely clear to me that if we just do something along the line, we would get similar results. That's not clear. Yeah. We can certainly, for example, if you have gauge fields, we can integrate gauge fields along the line, but that's the same as integrating the flux, the magnetic field over the surface. Yeah, so I'm not sure that just doing something arbitrary along the line would have similar scaling.
I wonder if the quantity you're talking about is kind of natural generalization of what people call the cusp anomalous dimension.
I've heard about that, although I need to learn more about it. I think this quantity shows up already, yeah, for Wilson, right?
Yeah, it's typically defined for line operators in gauge theories. You look at like a Wilson line with a kind of cusp singularity, and there's some kind of intrinsic. It's kind of like the small angle limit of this theta that you're talking about. And there's some kind of intrinsic scaling dimension associated to this cusp.
Yeah, I think it's definitely related. Could be just the same thing, but now we are doing it for
You're doing it more generally somehow, yeah.
A little more generally, like
Yeah.
when you don't have gauge field, but if you have global symmetry, you can do this.
Interesting.
Right.
One other question about your the first part of your talk, the
Sure.
gap phases. So you had this formula for the correction, the
You-
gamma. Yeah, that's probably fine. Yeah. So and you said, okay, in general, we don't really know what these PAs are. That depends on details. But I guess what I'm asking is, say we're trying to be the most general situation. We don't want to make any assumptions about the spectrum being an entanglement spectrum coming from some CFT.
Mhm.
Would you still say that it has to be of this form? Like, because this suggests some kind of quantization. If I take the exponential of this correction, it's quantized. It can only be integer linear combinations of certain numbers, D.
Yeah, I think that's what I
Should we
was.
take that literally, or is that like, is there still some? Because I know there are these, these spurious entanglement entropy things, and does that, are you saying that those things have to be quantized in some way?
I'm not sure about the spurious. I guess, yeah. So the the spurious corrections could also arise for this kind of objects. Although I haven't thought much about this, but let me see. So. So I don't really know how to think about the spurious objects even for the entanglement entropy, even though we know they arise because.
So you don't have a simple. So you're not saying that this formula includes the all possible spurious connect. This is like non-spurious.
What is a spurious term?
So for topological entanglement entropy, there are these like counterexamples where you get some weird term that's not the logarithm of the total quantum dimension. And so what I was asking him was, it sounded kind of nice that he was saying, look, my result doesn't predict that it has to be that, right? So I was wondering, is it actually including the spurious entanglement entropy in here? And is he saying it's always quantized in some particular way?
Yeah, so first about the spurious correction. So if I remember correctly, the one example I know, there might be multiple different scenarios where you get spurious correction. The one example that I know is that you get a spurious correction when we apply, this multi-region, mutual information, three tripartite mutual information prescription to calculate the correction. And the spurious correction only shows up there. Okay. If we, for example, use different ways to calculate this topological entanglement entropy, say on a cylinder, without any corners or anything, then the spurious correction does not show up, as far as I know. So it could be similar here that one might get spurious corrections with certain prescription to extract this gamma. But for other prescriptions, we can avoid the spurious correction and only get the piece that we are really interested in. So I think the spurious is kind of scheme dependent, which scheme we use to extract this correction. Yeah.
Okay.
But the result does not consider the spurious, just simply thinking about that.
Okay. Thanks.
Sure.
Is there a question on Zoom?
Yeah. Hello.
Hey.
Thank you for the nice talk. And may you go back to the slide for the calculation for the Renyi entropy?
Maybe you mean this slide or?
Yeah. So maybe it is a naive question. So is there any relation between this defect operator and the twist operator that we use to compute this Renyi entropy in the 1+1 dimensional CFT?
Yeah, so this defect operators, if we point to the boundary of the region and think about it on the, okay, maybe actually, I think it's better to use this picture. So, wow, it's already here. This picture. So if we now think about this in that example of replica symmetry, Renyi entropy, then this line here is a twist operator that I think that's a twist operator that you mentioned in the 1+1 CFT.
I see. So basically, can we say that because when we have the different angles, we can also have many different twisted operators. So can we say that probably there's a one-to-one correspondence between the twist operator on the boundary and the defect operator that you are using?
So I make sure that I understand the question. So there are multiple different defect operators. I mean defects, multiple types of defects in the bulk at least, which correspond to multiple different superselection sectors on the boundary with the same sort of twists, but there are still multiple different superselection sectors. And the Randi entropy is from, it calculates a particular sector, superselection sector of the twisted Hilbert space. I think that's my understanding is.
Thank you.
There are no more questions. Let's thank Professor Cheng again.
Thanks, Mom.
Great to see you.
Thanks. Sorry, I have to go. It was a nice talk. Thank you.
Thank you.